Unit 6, pages 130 to 140, Electron Configurations. The off-bow principle explains how electrons arrange themselves into the available atomic orbitals. This arrangement of electrons is important because it accounts for all of the chemical and physical properties of the elements. There are two key principles that determine the arrangement of electrons. One, the Pauli exclusion principle. Each electron must have a unique set of quantum numbers. This is the Pauli exclusion principle. How many electrons can be located in a 1s orbital? A 1s orbital has an n equal 1, L equals 0, therefore an m sub L equals 0. The possibilities for ms is plus 1/2 and minus 1/2. According to the Pauli exclusion principle, each electron must have a unique set of 4 quantum numbers. The only way electrons can have a unique set of quantum numbers in a 1s orbital is if you have 1, 0, 0 plus 1/2 and 1, 0, 0 minus 1/2. No additional electrons can be placed in a 1s orbital with a set of quantum numbers different from these two, so only 2 electrons can be placed in a 1s orbital. The same idea applies to all orbitals. Note the diagram here where you can quickly see the violation of the Pauli exclusion principle, because here we have an up 1/2 and a minus 1/2 spin, but here both of them have a positive 1/2 spin, which would give both of these electrons identical quantum numbers, which is impossible. The consequence of the Pauli exclusion principle is that at most 2 electrons can be placed in an orbital and the spins must be opposite directions. 3 electrons cannot be placed in the same orbital because it violates the Pauli exclusion principle. The 2 spin-up electrons both have the same identical set of 4 quantum numbers. Now we're going to look at electron configurations of hydrogen, helium, lithium, and beryllium, and they're found on page 133. Electron configurations are the way in which the electrons are arranged in the available atomic orbitals. The orbitals are arranged in energy with the lowest energy 1s orbital at the bottom. For each element, take the number of available electrons and put a maximum of 2 in each orbital with opposite spins. Start at the 1s orbital and go up in energy to the next highest orbital until all the electrons have been arranged in the appropriate orbitals. This is the lowest energy or ground state electron configuration. Other electron configurations with higher energies are possible. A configuration that is higher in energy than the ground state is called an excited state. So the 1s orbital is considered the one with the lowest amount of energy, and as you go up the orbitals to 2s, to 2p, to 3s, etc., the energy of the electrons is increased. Hund's rule. When filling electrons into p, d, and f orbitals, there are several choices for how the electrons can be arranged. So since these are of equal energy to one another, you're going to place them one at a time in each orbital before pairing them up with the opposite spin. So this would be a violation of Hund's rule. Paired spins, unpaired spins. Paramagnetic. In lithium, the electrons in the 1s orbital are paired with one spin up and the other spin down. The electron in the 2s is unpaired. Atoms with unpaired spins have magnetic moments and are called paramagnetic. In helium, all of the electrons are paired, resulting in almost no magnetic moment. When all of the electrons have paired spins, the atom is called diamagnetic. Hund's rule says for degenerate PDF orbitals, fill electrons one per orbital with the same spin until all the orbitals are half filled. If there are more electrons, then begin to pair them 2 per orbital with opposite spins. This minimizes the repulsions between electrons, which creates the lowest energy electron configuration. Hund's rule says that lowest energy electron configuration will have the smallest possible number of paired electrons per orbital and the maximum number of unpaired electrons per orbital. So the configuration up, up, up is lower in energy than if you have paired off and then a single. So here are some examples of carbon, nitrogen, oxygen, and fluorine, where we start adding the electrons one at a time into the orbitals before we begin to pair them off. Writing electron configurations. Electron configurations are a notation for showing the arrangement of electrons in all of the orbitals. The electron configuration for lithium is 1s2, 2s1. The orbitals are written in increasing energy. So we have 1s2, 2s1. And so we'll write it in this way as an electron configuration. This is an orbital notation. And then each of these represents our orbitals, and you can have a total of 2 electrons per orbital. In order to write electron configurations, you must memorize the order of the orbitals of increasing energy. The easiest way to do that is to use the periodic table as a guide. So note that you have the S block, D block, P block, and F block. When you have your S and P blocks, the row number equals the energy level. So this is row number 1, this is row number 2, row number 3, row number 4, etc. Notice the D block is the row number minus 1. So when we are on row 4, when you enter the D block, it's not going to be 4D, it's going to be 3D. And notice that the F block functions the same way, except it's the row number minus 2, because we don't start with the F block until row number 6. And so it would be 6F, 6S, 4F, and then 5D, and then back up to 6P. Example 6.40, write the electron configuration for germanium. Here's where germanium is located on the periodic table. So our electron configuration begins with the inclusion of the first row, which will give us 1s1, 1s2. And then the second row, we have 2s1, 2. Then go all the way across to 2p, 1 through 6. Now we're on row 3, 3s2. Across to have 3p6. And now we're on row 4, 4s2. And note that after 4s2 we go to the D block, which is going to be the row number minus 1, so 3D. We go all the way through the 3D block, so we have 3D10. And then finally, we're in the 4P block, and we're going to go 4P1, 2 spaces to get to germanium. So it will be 4P2. And this would be the electron configuration for germanium. Remember that in the sublevels, S, P, D, and F, you can have a total of 1 orbital or blank, 3 orbitals or blank for the P, 5 in the D, 7 in the F, and each orbital is going to contain 2 electrons maximum. Note as a point of checking, each of your superscripts should add up and the sum total should be equal to the number of electrons total that your atom should have, which in a neutral germanium should be 32. Knowing how to look at the periodic table to identify electron configurations is a very powerful way of quickly identifying the electronic properties of an element. Note how fast these questions can be answered just by looking at the periodic table. How many unpaired electrons does germanium have? All of the electrons must be paired except the ones in the last unfilled orbital. According to Hund's rule, both of the 4p electrons are unpaired, so the answer is 2. Which element has 5 electrons in the 5p orbital? Iodine. Which of these elements has a filled 4d orbital, gallium or indium? And you can say indium. So shorthand notation, also known as noble gas configuration, is where we go to the previous row number, which in our case, germanium is on row 4. So we go to the end of row 3 to find the noble gas, which happens to be argon. We place argon in brackets, and that's going to be the abbreviation for rows 1 through 3. And then we continue from the beginning of row 4 on to where germanium is located on the periodic table. A shorthand notation is sometimes used. The last filled noble gas electron configuration is written followed by the rest of the remaining orbitals. For germanium, argon is the last filled noble gas with the configuration 1s2, 2s2, 2p6, 3s2, 3p6. So the electron configuration for germanium in shorthand notation is going to be argon and then 4s2, 3d10, 4p2. The inner core electrons are represented by argon. The outer electrons, 4s2, 3d10, 4p2, are called the valence electrons. The valence electrons are involved in chemical bonding. Although in this course, most of the molecules will not use electrons in atomic d orbitals when making bonds. Valence electrons are the outer, highest energy electrons involved in chemical bonding. For germanium, these would be the 4s2, 3d10, 4p2 electrons, or more specifically, the 4s2 and the 4p2 electrons. What is the shorthand electron configuration of rubidium? What orbital is the valence electron in? So here we're going to find rubidium is at the beginning of row 5. So at the end of row 4, I'm going to use the noble gas krypton in brackets. And then I'll go back to the beginning of row 5 and find that rubidium is in 5s1. And so we have krypton 5s1. And so this is where the valence electrons are located, and you can see that we have only one valence electron in rubidium. Electron configurations of transition metals. The transition metals have several exceptions where the expected electron configuration is not observed. The s and d orbitals are very close in energy. As electrons are filled into the d orbitals, the energies of the orbital shifts from electron-electron repulsions. This creates unexpected electron configurations. The easiest way to remember where the exceptions occur is to remember that the d orbital likes to be half filled and completely filled. When possible, an electron is removed from the s orbital to make the d orbital half or completely filled. So here are all the expected noble gas configurations of these elements, and you'll see when we get to chromium, there's an opportunity to move one electron from the 4s over to the 3d, in which case we would have a half-filled s and we'll have a half-filled d. And then down here, when you get to copper, we could shift this electron over to the d sublevel, giving you a half-filled s and a full d. So these are the only two scenarios where you should be shifting electrons in order to create either a half-filled or a filled sublevel. Note that molybdenum follows the same behavior as chromium and silver follows the same behavior as copper. There are many more exceptions in the D and the F block, but these are the only 4 you're required to know. Here's your note card for this section. First of all, the off-bow principle, electrons enter orbitals of lowest to highest energy. The Pauli exclusion principle, no two electrons can have the same quantum numbers, and it would look like this if they were to violate that rule. Hund's rule, for degenerate orbitals, fill electrons one per orbital with the same spin until all the orbitals are half filled, then begin to make the pairs. If you have a paramagnetic electron, it's alone in an orbital, and diamagnetic means they're paired off. Valence electrons are found in the highest energy level, and they are involved in chemical bonding. And then know the 4 electron configuration exceptions. Chromium and molybdenum will move one electron from the s to the d, giving them both half-filled orbitals. Copper and silver will move one electron from the s to the d, giving you a half-filled s and a full d sublevel.